Hi, everybody. Welcome to my talk. I'm Pavan Churaga from Arizona State University, Associate Professor in the School of Arts, Media Engineering, and Electrical Engineering. I also direct the Geometric Media Lab at ASU. The topic of my talk today is topological methods for robust human activity modeling. I'll try to keep the talk limited to 30 minutes, so it leaves us some time to ask questions, and I'll be timing myself carefully. So the purpose of this talk is to provide a slight overview of the kinds of things we have been doing at the Geometric Media Lab, employing topological methods in multimodal human activity modeling. I will start with introducing the problem space to you, trying to convince you why the problem is challenging. What do we really mean by human activity analysis? Why do topological methods make sense? What we have done in translating topological methods to practice, and what are the key bottlenecks that we face on the practical side, and how we are trying to overcome those. So what do we mean by human activity? It seems like the word human activity can mean pretty much anything, because human activity is the sum total of all the outcome of human existence. So that's too grand a problem statement. But in practice, when we talk of human activity in areas like computer vision and health analytics, we mean physical human activity, which is human movement tracking through a variety of sensors like video, depth sensors, motion capture, wearable devices, so on and so forth. But even within that restricted definition of human activity, which is physical human movement, there can be a variety of further subdivisions and further spectrum of techniques. I have found it useful to think of human activity along a few fundamental dimensions. And here I'm showing you some very simple three-dimensional view of what human activity analysis encompasses. On one axis, the vertical axis, you have temporal extension of the activity. On the horizontal axis, you have spatial extension of activities. And on the z-axis pointing outside the screen, you have the number of people involved in the activity. It's a very simple categorization, and many events of interest, many kinds of data sets of interest fall somewhere in between these, in this space. So let's say at the very origin, where we are talking of humans, single human in a scene, doing a small action which lasts maybe a few seconds long, and it's happening in the same physical location, what we might call as primitive actions is one set of activities we're interested in. These kinds of actions are of interest in health analytics and behavior change problems, and also in surveillance kinds of scenarios, but surveillance can extend across space and time and people. If you go to the vertical side, we have also actions which are still done by a single person, like this action of someone conducting an orchestra. At least the conductor is a single agent, and they are located in the same physical space, but then their actions are temporally extended. So it's a very complicated action. Sometimes it's been thought of as conjunctions of primitive actions. We like to think of actions as dynamical systems, and whether it's short or long, you can think of them as dynamical systems on a long time frame if needed. Then we have actions which happen maybe in a large physical space, like activities in a grocery store. Maybe it's one person, maybe it's a group of people, but the physical location is big. So there is an interesting, it may be the same primitive action. Maybe you're just walking, but you're walking all over the store. But where you walk makes a difference about what's happening in the scene. So there is some contextual information that's needed. And then the third axis is coordinated group activities. So performances, and performances is only one of the ways in which you talk of coordination, but even in regular daily life, we engage in group behavior, activities in a classroom, activities at a bank, and there is some kind of coordination synchrony that occurs. So in this broad spectrum of human activity, we are of course interested in all of these variations, but then it turns out that it's a very challenging space, and different methods seem to make sense in different extremes of these axes. And we will talk about where topological methods make sense and what are the benefits and the limitations of topological methods, and why they make sense. So as you can see, modeling activity in its grandest sense can be a very hard problem, as there are multiple ways to define the same activity. In the examples that I showed you earlier, when I said things like activities at a bank, if you drill down further and you say, well, let me define the activity of drawing money from the ATM, you can just imagine the variations that are possible. Are you talking of the ATM outside a parking lot? Are you talking of drawing money from a teller inside the bank? What are the interactions that could happen between a person and another person at the teller? There can be enormous amount of semantic variability, which of course manifests also as statistical variability, but we like to call it semantic variability because it's more symbolic at that level. And then there is a multitude of confounding factors, which primarily comes out because of physical things. Once you choose a sensor, let's say a video camera, then the angle of view, the frame rate of the camera, the lighting conditions in the scene, all these things change the data that you measure, even though the activity may just be the same thing. So there are lots of physical confounding variables, which lead to variations in what's measured. And then of course, there are multiple ways of even sensing. The same activity could be sensed from a video camera or a wearable device, or a combination of the two, or maybe other things like even audio sensors and pressure sensors. So we are interested in methods that generalize across sensing modalities, and that makes it hard. And of course, the possible end tasks are numerous. We are interested in recognition of activity. We are interested in understanding the quality of movement in health applications. We are interested in regressing movement data to other continuous valued attributes, such as health indicators, biomarkers, so on and so forth. So the end task is variable. It can range from classification to regression to clustering to even other kinds of attributes like periodicity detection. So the end tasks can be diverse, and no single representation works across all these tasks. So these are things which make modeling activity really difficult. So in the realm of single human activities, whether short or whether it's long, the temporal dimension that I mentioned, single human activity, primitive actions, or even more complicated actions, but done by a single person, often can be thought of through the lens of dynamical systems. There is a rich history behind the use of dynamical systems language in understanding human activity. The intuitive idea is simple. You think of the human body as basically, consisting of certain states, which include the location of the joints, the forces that are, occurring between the body and the floor, and other kinds of things which are not necessarily measurable, but these are all the states that define the movement. But then you attach a sensor, you make some measurement, maybe a wearable device, maybe a camera, it's measuring some subset of the states. And then you have these measurements that are changing over time. And you want to understand something about either, you want to either classify the time series, or you want to estimate parameters of the process, the dynamical process that generated the time series, and use the process parameters to classify. It's a good way to think about primitive and complicated actions, because it gives you a way to think of generative methods, which can then be used to create some invariant representations. Once you think of dynamical systems as a framing, you get certain invariant properties, which is, let's say you're walking and you estimate a dynamical system that synthesizes walking, that the model parameters are invariant to gait phasing. So if you're only interested in signal matching, then you have this additional problem that the same action can have different initiation points, right? So if you're walking, do you initiate from the left foot or the right foot? And which point in that phase did you start measuring? All these things change the signals recorded, but the model parameters are invariant to those things. And our research has also shown that there are other kinds of invariances that you can either explicitly build in, or you have some robustness to those factors, including time warping, including small amounts of viewpoint variations. So dynamical systems ways of thinking allow you to get some invariance and robustness to some measurement factors. So there is a rich history around it. But here is a problem. When you think of the same action with measured through maybe slightly different sensors, you're making measurements that are different projections of the state space. An illustration of that is seen in this animation, which is from a paper by Sugihara et al., which illustrates nonlinear dynamics. And this is the very classic Lorentz attractor. What you're seeing is a three-dimensional dynamical system, which is evolving in the 3D space. There is some nice smooth properties about the forward map that maps the current state to the next state. But then you start attaching sensors, low dimensional sensors, measuring maybe one joint. Maybe this is a three joint action. And then you're measuring one joint at a time. You start seeing different signals because you're measuring different parts of the state space. So this is a slightly empirical way to think about what happens if you're walking and you're attaching an accelerometer to the chest versus attaching an accelerometer to the waist. The signals for the same actions will look different. And why? Because you're measuring different projections of the true state space. So how do you get that level of invariance, which is invariance to different measurements? Now that's a grand challenge, and the dynamical systems framing allows you to think of, again, some ways to account for that, and that's where topology comes in. So here is an example. This slide is illustrating this method called delay embedding to recover a surrogate of the dynamical state space through measurements. The idea is simple. No matter what measurements you make, there is a process called time delay embedding, which allows you to get a topologically equivalent version of the true state space. So in theory, and we haven't yet fully proved it in practice, but we're getting closer to showing some of those favorable properties. In theory, if you have a dynamical system and you're measuring slightly different measurements of states, under the assumption and the true conditions are stated in a famous theorem called Tackin's embedding theorem, you assume that all the variables are entangled, everything affects everything else, the measurements are smooth, the forward maps are smooth, and invertible, there are some very specific conditions. Then, if you have differing measurements, you're measuring slightly different projections of the state space, you can recover topologically equivalent versions of the true manifold in which the states are evolving. Why is that relevant? I'll soon give you an example. This is, we've found this to be an extremely relevant framework for a class of applications which we started investigating a few years ago in human movement quality assessment. Motion capture of, let's say, a few joints of your body is a very important component of modern physical therapy. And if you suffer from stroke, there is a specific set of prescribed exercises that are being considered by physical therapists, like reaching for an object on a table. But the quality of that action is measured, current standard of practice says the physical therapist will look at your movement and make a qualitative assessment. But the practice is moving in the direction of putting sensors in place, like motion capture, and measuring some objective properties of the movement. One of the problems in motion capture is you can never mark the same location precisely ever again. There is no such thing. So if you attach a sensor to the wrist, the next time you attach it, there will be a slight amount of misplacement. And the signals that you record thereby will look always a little bit different. But if you do this process of time delay embedding, the theory says that you will start recovering some topologically equivalent versions of the movements of, across these different measurement methods or different placement, of the sensor. But then how do you describe that topologically equivalent space? So that's where we're headed. Classically, in the dynamical systems literature, if you had to describe these recovered attractors, one of the common ways in which they did it was through a method known as Lyapunov exponents, which measures the divergence of closely spaced trajectories in the state space. And that is shown to be a topological invariant. So that has been used. The trouble is, even though it's an invariant, you have to understand that invariance by itself is a very small part of the story. You want to have representations that are invariant to these nuisance factors we're talking about, but we also want representations that are actually useful for given n tasks. The n tasks we are interested in are either these classification problems or regression problems. So invariance by itself is not enough. You need usefulness for the n task. And what we find is some of these classical invariants like Lyapunov exponents, correlation dimension, correlation integrals, these are words that have been around for a few decades. They are invariants, yes, but they are not very useful for the tasks we're interested in. So that motivated us into developing more and more sophisticated features which give us the invariance to this topological deformation, but are also somewhat useful. After some initial empirical investigations, we took a divergence into, we took a detour into some shape theory methods. We were looking at describing the attractors through some shape-related properties, and naturally we came across this body of work in TDA, topological data analysis, and that was, that changed our whole game. And of course, this audience, TGDA, does not need an introduction to topological data analysis, but here are a few slides just for completion. Yes, the idea is you have a point cloud, and in our case, the point cloud that we have comes after we go through this process of time delay embedding or something like that, depending upon the sensor we have. Sometimes when we talk of video sensors, we think of the point cloud generated by video features as the point cloud. So there are slightly different ways in which we get these point clouds. But once we have the point cloud, we're trying to describe its shape through the lens of topological methods, which gives us some robustness to deformations, which is what we're trying to get at. Of course, the process is through this idea of filtrations. You're putting these little balls around the points and tuning this parameter, the radius of the ball, and tracking the appearance and disappearance of cycles and connected components and voids and so on and so forth, higher dimensional features. And the same things can be done with raw time series. You can do scalar field topological methods that scan through a range of values and track the appearance and disappearance of connected components and so on and so forth on the real line. So very sophisticated methods have been developed by the TDA community, and we are investigating their applicability one by one. So what we find, again, this is just a quick primer on TDA, not necessary for a talk in the topology venue here. Here is how we've used it. So here is an application of the TDA methods to some data in some synthetic examples. So in the middle of the plot here, you're seeing the Lorentz attractor and this other attractor whose name is missing. These are two standard attractors that are commonly used in the Rossler attractor, the Lorentz and Rossler systems that are used in dynamical systems theory to sort of validate the methods you're talking about. Here are time series associated with these dynamical systems measured across one axis. Actually, these plots are not the true dynamics, but these are the reconstructed dynamics from measured time series. And then their persistence diagrams, which in this case are showing the connected components in the cycles as they appear and disappear. And you can see that the significant components are here at the very top. These are the noisy components which we want to ignore. And we have one big cycle detected here, significant, and we have two significant cycles detected here. So these are beginning to get useful information about the dynamics and quantify the shape-related properties. We find that it actually also works with real data. Here is, at the bottom, is recognition accuracies for an activity recognition experiment where we had access to motion capture data, 50 roughly joints of the human body. And we did this process for every joint individually. You would take each joint, do its delay embedding, recover an attractor, describe its shape by TDA methods, and do it across all the 50 joints. And then a measure would be, a distance measured in that space would be some combination of the measures across the persistence diagrams over the joints and averaged out somehow. So we find that at the very bottom is accuracies using the Wasserstein measure on persistence diagrams averaged across joints, does very well. And some of these other numbers that you're seeing The first row, when you say chaos, is the classical invariance, the correlation dimension, the correlation integral, the Lyapunov exponents, concatenated. We have roughly 8 to 10 such invariants known. And they are known invariants, but they don't seem to work very well for classification problems. These other methods along the way, we invented them, where we were looking at some shape-related methods inspired by how people talk about point cloud shape features in computer vision and graphics. Once you have a point cloud, let's say, people talk of things like shape distributions. You take random points on the surface, compute some shape measures, and look at histograms. So we were looking at some of these graphics-inspired ways to index shapes, and they sort of do a good job too, but they don't have the theoretical niceness that comes with TDA. And we are also able to do better than them with these principal methods. And of course, we have a pretty good confusion matrix that attests to the strength of the TDA features. So this is a video that I'd like to play, which shows our applications to stroke rehab. Again, the little shiny dots you see are motion capture markers. And we believe, we work with physical therapists and clinicians who are in the space, that this is the future of physical therapy, where you're attaching sensors to the body, and the practice keeps shifting. Sometimes people go from motion capture to wearables, and then they come back because the quality of the sensing is always a little iffy in these situations. And what sensor will get deployed 10 years down the line is unknown, but the methods we are pursuing seem to generalize across sensors. So that's the good news. So we are looking at trying to quantify the quality of movements like reaching, as you can see here. And here are some quick results that compare a few different things. So we are looking at correlating. Now this is a problem of regression. We want to regress our shape-related features of the human movement trajectories after reconstruction of the retractors to some other scores which correlate with therapist impressions of movement quality. In practice, there are, in biomechanics literature, people talk of very specific measures of human movement quality that range from things like smoothness of the movement, jerkiness of the movement, curviness of the movement, which are physically interpretable. And there are, we worked with about 30 such attributes which had a physical meaning. And they ranged from, as I mentioned, peak speed, the velocity profile shape, and curviness, jerkiness, all these things which are very understood and point measures, so to speak. And they do well. We have this regression model which regresses these shape-related properties directly, and that does much better. And the regression coefficient is much higher than some of these others. And what we also find is we were able to do this dynamical features only from one marker, from the wrist. Whereas some of these other features, the attributes that we're talking about, these other columns, were computed from several markers. So the attributes that were computed just from one wrist did very poorly. Computed from 14 markers did very well. But then our dynamical features are also computed from just one marker. And that is also beginning to tell you that through this process of delay embeddings and recovering state spaces, we are able to recover the properties of the full state space without having access to all measurements. So the combination of this dynamical systems way of thinking combined with the topological ways of describing these dynamical state spaces is a very powerful tool in this space. So the applications I talked about so far included, arguably the sensing made things a little easier. The sensing was either a wearable device or it was motion capture, which removed a lot of what I would call nuisance variables, like lighting conditions, viewing variations, so on and so forth, which occur in computer vision. So we wanted to go from these early successes of working with sensors, which gave us, some sort of more direct measurements of what we needed, to completely image-based ways of looking at human activity, image and video-based methods. And we ran into some really difficult situations there, and I'll talk about that a little bit. So when you try to apply these methods to direct video-based tracking of human movement, you have to make a few decisions. Human movement, when measured in video, is complicated because the angle of the camera will make things different. So here are examples of the same actions So check, watch in 3 different views, sitting in 3 different views, walking in 3 different views. And then there is time series of these frames. So how will you compute TDA? TDA of what? So you have to make some decisions. One of the things, we tried a few things here. We said, let's compute some image-based features per frame. So you sort of assume that there is some tracking information there. You're assuming that there is a bounding box that bounds the person. You're extracting some features from that bounding box. So you have a time series of those features. You can then do delay embedding per dimension of that feature again, or you can consider already the feature space and you're looking at some kind of shape that's emerging in the feature space, and you can do TD on that feature space. So we tried these different variations. Some things just work better than others. There is no clear guidance we have at this time, but they all work somewhat equivalently. You can treat the features themselves, the point cloud that comes by embedding these images into the feature space directly as the basis to compute your TDA features, or you can do one more step of going dimension by dimension, thinking of them as dynamical systems and doing TDA on those recovered attractors. We haven't yet had a clear answer as to which way to go. So, but either way you go, you have to deal with other bigger problems, which is image data suffers from significant amount of nuisance variables, which manifests itself under this topological lens. It manifests itself as topological noise in that point cloud that you're looking at, because you're making a lot of assumptions. The same action, lighting fluctuates in any real data set. The ambient lighting always is a little fluctuating. And as you move around the scene, you're casting shadows, and different parts of your body are well lit and some are not well lit. So these variations are hard to model, and they change the point cloud. We assume tracking is good. We assume that the bounding boxes are nice and where they should be, but there is no standard answer as to tracking. Tracking introduces its own tracking errors. There is always some jitter, and it is sometimes referred to as registration errors, and that changes the features. Camera sensors themselves introduce some variations. Camera sensors often have some auto white balance correction, and they have dynamic ranges which keep adjusting on the fly. So any data set that you download off of the internet will have all these implicit variations, which to your naked eye will not be visible, but they all make a difference on the point clouds you're getting for TDA analysis. So there is a significant amount of topological noise that gets added when you talk of applying these methods to image and video data sets. Here is, an example. One of the ways in which we decided to deal with this perturbation issue, we actually found that when you computed these persistence diagrams, they had this perturbation show up in the persistence diagram. Same action from a slightly different person, slightly different viewpoint, seems to perturb the persistence diagrams. There is some level of robustness, but there is some perturbation. You can do a few things. You can assume that the perturbation is so small that it should get covered in the within class variance. We found that it helps to actually use that perturbation to your benefit. The way we robustified all of it is we took the persistence diagrams that came from the raw data set, and we actually perturbed them further. And we took these perturbed persistence diagrams and summarized them compactly through subspaces. So here is a processing pipeline, image, maybe a short segment of video. You would get a persistence diagram corresponding to it. We perturb them all. We shift all the points a little bit. We add some translational noise, because we know that that is the effect of real conditions on the images. The effect of lighting, viewpoint, tracking errors on the images results in this kind of translational noise in the persistence diagram. So we sort of artificially induce it, sort of like data augmentation that is popular now in deep learning. So we introduce these effects in the persistence diagrams, and then we collapse that set into a subspace. The reason for collapsing that into a subspace at the beginning was pure computational simplicity. We don't want to deal with a stack of PDs. And of course, from the PDs, we sort of compute these more continuous representations, the persistence landscapes, and then we create the PC of that set of persistence landscapes, persistence images. The reason why we did that initially was pure computational simplicity. Subspaces compact, you get invariance to other things, permutation invariance. It doesn't matter how you order these PDs. It doesn't matter how the order of which the way you chose those perturbations doesn't matter. And then once you make it a point on, once you make it a subspace, you think of it as points on a Grassmannian manifold, and we have closed form expressions to compute geodesics using subspace angles, very fast computation. So we thought, let's try that. It gave us some unintended benefits. It gave us robustness to this shifting problem of the persistence diagrams. We had a nice expression to compute geodesics on the Grassmannian as a way to measure distances between these tagged and summarized persistence diagrams. And greatest of all, when we put our minds to it, we actually found we were able to develop a stability result. The distance of these, the distance between these subspaces as computed on the Grassmannian was upper bounded by some very complicated nonlinear relationship, which involved the one Wasserstein metric also on the right-hand side. And that's a good stability result to have. It means there is some niceness to this way of doing computations. So here is a quick sanity check. We wanted to see the effect of actual additive noise on a visualizable point cloud, a 3D point cloud here, let's say the Schreck data set. You add some additive noise to the point cloud, and here is the translational shifts that you're seeing on the right-hand side of the persistence diagram. So how do our perturbed subspaces and the Grassmannian metrics perform? Here is a quick result table, very big table. Key lines are the top 3 and the bottom 2. The top 3 are persistence diagrams and the classic 1 Wasserstein, 2 Wasserstein, and the bottleneck distance computed over individual pairs of diagrams and a 1 nearest neighbor classifier. They do very well, 98%, 95, 97, great. But there is a huge time complexity in computing those Wasserstein metrics. When we do our approach, which is we take the PDs, we perturb them, and for the whole perturbed stack, we fit a subspace, and then we compute Grassmannian distances. We do very well too. I mean, in many ways, some ways you could say we do better than the classical methods. But the bigger benefit we have is in time, 2 and 3 orders of magnitude, or maybe 2 orders of magnitude faster than these gold standard methods. And the Grassmannian metrics are super fast to compute. There is no combinatorial problems to solve with subspace angles solvable by a simple SVD, very fast. So that was, for a quick sanity check. When applied to the full Schreck 2010 data set, which had 200 shapes from 10 classes each, we found similar results. We are very competitive to the state of the art at a much smaller fraction of time needed to compute these metrics. So that was good. Now with that sanity check in place, we went back and applied these methods to the video problems that we started with. We wanted to apply this to view invariant video activity analysis problems from image data, where this perturbation problem is very obvious. And we compared a ton of methods. We used this data set called the Xmas data set, which is a standard data set from a few years ago. And there's many benchmarks in that area, very clever choices of features that are view invariant, but nothing guaranteed. Of course, I mean, TDA on its own is not enough. You have to sort of do some fusion, but we were able to boost performance in fusion with other simpler features like self-similarity matrices computed from hog features in time. That's a dynamical descriptor by itself. So we sort of do okay, but we do better in fusion with other features, and we're able to robustify some of these features like optical flow. In addition, with the fusion was done through kernel methods. We can have kernel-based fusion methods. So we were able to boost performance not on its own, but in fusion with other methods. So with that, I want to conclude soon with some speculations. We have been looking at asking, some of these experiences told us that TDA methods by themselves may work when some of the sensing modalities are nice, such as wearables, motion capture, maybe applied to 3D shapes, yes, but applied to image and video data by themselves, they are not capable of providing the greatest of performance. They need to be fused with other features. And then the big elephant in the room in this day and age is the features have to be learned from deep learning. So how do topological methods fuse with learned features? Should they be fused? If they can be fused, are there better ways of achieving compatibility? Can you actually even learn? We were pushing on that, and we're asking, can you actually learn topological features? And the reason why we want to ask that question is, first of all, topological feature computation itself can be expensive. And we'll show you some experiments quickly where we find that just concatenation, you take some topological feature, TDA-based feature, and then you just concatenate it to something, or just fuse it with some kernel methods. It's suboptimal. You can do better if the topological feature also comes from a deep learning architecture. It may not be gold standard, but it seems to improve compatibility of fusion. So here is some quick motivation. Now here we are sort of moving away from the image, from the video activity problem, but these are standalone speculations which apply across data sets. We're taking these simple 32 cross 32 pictures and thinking of these pictures as point clouds in some of these methods. Some of these ways of converting pictures to point clouds was motivated by work done by Tamal Day. You take every pixel and you map it to a 3D space or 5D space where the RGB value is concatenated to the XY location. So you have a 5-dimensional vector associated to each pixel. And then you can compute some homological features from that point cloud. When doing it that way, computing the persistent homology features for these data sets took 2 days and 3 days. We want to shift it from taking that long to doing it in a matter of minutes. And our solution is to use deep learning architectures to actually learn to convert raw data to a topological feature. In our case, it's a persistence image. I won't have time to go into this in great detail. The idea is now, I want to be very careful in stating this. We are not promising that we can take an arbitrary point cloud in RD and spit out a topological feature with deep depths. No, we are applying it specifically to 2 kinds of data sets. One is pictures, where we implicitly want the mapping from a picture to the point cloud to come from this way of embedding a pixel into this 5D space. That's the thinking behind the process. But then given a picture as input, we can apply convolutional operations and bypass that way of doing things. Same with time series. If you have a time series, we can convert that, we can apply some convolutional operations on the time axis and do some nonlinear operations on it to regress a persistent homological descriptor, which comes through maybe a filtration process, maybe a scalar field topological filtration process. So we're assuming the input to be either a picture or a time series. We cannot take an arbitrary point cloud of unknown cardinality in some unknown dimension and create a deep learning neural network that works. That's not the claim. The claim is, as applied to pictures and time series, I think we can make some headway. So here are some very quick examples of what we can do through, so these are pictures on the top row, gold standard persistence images in the second row. The PyNet, we call this the PyNet, that our deep learning architecture learns to regress what it's doing. And then you can sort of fine tune it and it starts to get better. Same thing on a different data set. We are able to get a neural network to learn to regress, given an input image, a persistence image that comes close to what the gold standard persistence image should look like. We find that it's much faster. On a CPU, the PyNet can return these persistence images in a matter of hours, a couple hours, whereas the gold standard ways of computing those features would take 2 or 3 days. So huge reduction in time. And of course, on a GPU, it's much faster, but you can say it's not a fair comparison. But even on the CPU, we are significantly faster. What we actually find is, do they actually help? We are faster, yes, but we can't guarantee that it will be the exact same as the gold standard. But we find that it improves fusion performance, even though it's not looking like the gold standard PI. Here is an experiment on activity recognition on time series from wearable data. We are computing scalar field topological features. And MLP stands for a multi-layer perceptron. So you take a PI computed through gold standard methods and you plug it into a multi-layer perceptron. These are some F1 scores we have on 2 kinds of data sets. When you apply the same MLP on the persistence image generated by our deep net, which arguably is not the gold standard PI, but it's some approximation to the PI, even then, we actually do better. So the signal PI net is, the time series version of the pi net that I spoke about. It seems that the empirical finding we are coming across is learning to regress a homological feature or topological feature will not give you true gold standard features. They'll give you approximations. But when fused with machine learning, they seem to do better than the gold standard methods. So we are chalking it up to similarities in how classifiers work and how feature learning methods work. And because the processes seem to be similar, the fusion seems to be compatible. This is not a theorem by any means, but this is some engineering findings we're having. And we'd like to, of course, know why. And this is the community that can answer that question for us. Should we learn topological features through machine learning methods? And it seems like it's helping in fusion applications. So in conclusion, I'd like to say that topological methods do provide a very general purpose approach to think about robust modeling problems. Human activity problems are interest, but it seems like they are applicable to many kinds of data sets, especially when applied to human activity problems from carefully selected sensors like wearable devices and motion capture devices. We have had good success. From video-based sensors, it seems like by themselves, they do not have the necessary discriminative power or the necessary end task specificity. They need to be fused with other features. And when we get into the fusion realm, we are finding that fusion is enhanced when you actually learn topological features rather than just concatenate topological features that come through classical methods. So these are some ideas and conclusions. Happy to take questions and happy to collaborate with the community to find answers and make progress. So thank you very much for listening.